So hi all, it's a pleasure to be here and part of the DataShape team, where I'm doing, I started my PhD thesis in September under the supervision of Frédéric Chazal and Bertrand Michel, and I'm working on geometric inference for multivariate time series. And what I would like to talk to you today is kind of the first part of the project. So I'm aiming to do pattern detection using dynamic time warping on data that's coming from navigation systems. And so before diving into the core of the subject, I would also like to talk briefly about what I did in the past to kind of set the context. So I worked a bit on persistent homology, and in particular on understanding geometric realizations of persistent homology classes. I did this as a semester project during my master's, and my master thesis was on audio identification using persistent homology, so devising signatures of songs which would remain invariant after obfuscations of a song. And the aim was to apply these techniques to audio identification. So today I would like to motivate the problem of pattern detection and dynamic time warping as a tool to solve it. For those of you who don't know it, recall the definition of dynamic time warping, see a few, in my opinion, interesting applications, and finally look at differentiability of dynamic time warping and how the various problems that arise and how it's been solved. So my project is in collaboration with Sysnav, and it is a company which specializes in navigation systems, and who says navigation system means also positioning system. And so a few examples like the GPS, but each of them has some caveats, like for the GPS where the signal is not always available, or for inertial sensing where there are integration errors, or magnetic positioning, which in itself is not sufficient. So more and more popular are hybrid systems where you can combine, for example, different sources of information like inertial sensing and magnetic positioning with extended Kalman filters. So to show you an example, for heading estimation, you can use data from a gyroscope, which gives you the angular rate, and you can integrate that and correct the estimates. What you obtain would have a drift due to the errors, and so the idea is to correct these estimates with data from, for example, accelerometers or magnetometers, thus having more precise estimates. And yes. So I'm more interested in, so this was a navigation system for pedestrians, but I'm more interested in vehicles, and in particular cars. And so here we have the problem that actually the moving parts in a car induce perturbations on the measurements produced by a magnetometer. So you can imagine that there are many moving parts, and the position of each influences the measurement. So the techniques that were applicable for pedestrians, for example, might not be directly applicable, since the variance of the measurements will be significantly higher, for example. However, the promising aspect is that precisely these perturbations might encode some quantities related to the motion of the vehicle. So let's see an example. Here you can see the piecewise linear curve obtained by connecting successive measurements of the magnetic field. And so this is a curve in R3, and you can see two things. So first, most of the measurements roll around a torus. They do small circles around the hole in the middle. And you can also see an outlier trajectory, which might be due to the car passing a big metallic object or underneath high tension lines. So to see how it looks like and whether we have the hope of recovering anything related to the, for example, velocity and heading, let's look at how this looks in time. In particular, for easier visualization, let's look at the norm. So looking at this curve, for example, at the right, we can see that the vehicle might be stationary at the end, right, where there is no there are no fluctuations in the measurements. And you can also recognize other segments where the vehicle is probably stationary. And there are also other periods of times where the local mean varies and there are oscillations of different magnitudes. And if we zoom in on the oscillations, we can actually discover that the time series is a concatenation of a pattern. So here it's a rather simple pattern where you have one prominent maximum followed by a succession of small local minima, then goes down and up again. And so looking from left to right, the pattern is first a bit stretched, and then at the right it's compressed, meaning that the velocity of the vehicle probably changes, and so the frequency of how the wheels turn increases from left to right. So we aim to we place ourselves in this in a one-dimensional case. So we have a vehicle moving on the real line. So from time 0 to time t, and its position is encoded by x. And we have an observation function which models the observation of the magnetic field or the norm of the magnetic field. And we'll assume it's one periodic. Then what we see, the observations given by the magnetometer are actually samples from F composed with X. To show you a synthetic example, from top to bottom, you have the displacement in time, the observation function, so the pattern, let's say, a few repetitions of it, and at the bottom, the composition, so the continuous version of what we would observe. And so looking at the first top graph, you can see that in this example, the vehicle first moves at a certain speed, then decelerates and accelerates near the end. And you can see this reflected on the bottom graph where the middle part is stretched compared to the first part, and the part on the right is just the same pattern but compressed. And so actually our aim is to study the velocity of the vehicle, so the first derivative of x, given only the observations. And our first idea, was to look for a periodic, so for this pattern present in F, and a natural notion which comes up in such a case is the dynamic time warping discrepancy, which we move to. So it was first introduced for spoken word recognition in way back in '78, and it has witnessed many applications since. And so I'd like first to give you a brief overview of these applications, present the definition, and then we'll dive a bit deeper into application 2 and 3, and then move on to differentiability. So for audio synchronization, the idea was that we had different, so the authors had different tracks, so different realizations of the same song. Think of a concert version and the studio version of the same song, and they wanted to basically cluster them according to that similarity and recover the clustering given by our two tracks, two realizations of the same song. There was periodic detection in string, where you have a string which is a concatenation of a pattern with some modifications. And then we'll see an example of time series classification. But first, maybe the definition of dynamic time warping. So I'm not assuming you're familiar with it. So for two signals represented, U and V, represented by vectors in Rm and Rn respectively, we will consider paths, so a path rho, which traverses both signals, starting from their beginnings. So row of 1 is 1, 1, and which ends at their ends. So row of k is mn. And we require that the path is does not go backwards and also traverses all elements of both signals. So here in condition 2, we require that the difference between consecutive terms is between 0 and 1. So now we can define the cost of such a path. So the cost of warping U to V, given a cost function. It's just a sum of costs of, let's say, you can think of distances between elements from U and V. And so we take them at the indices given by the path. To give you an example, so to conclude the definition, the dynamic time warping problem consists of finding the rho star, which will realize the minimum of this cost, and the dynamic time warping discrepancy is just that cost. And to show you an example, if you compare two signals under the Euclidean metric, well, first they have to be of the same length, but even if they are, you might not really be comparing the same elements. Whereas if you look on the graph on the right, where you're using the dynamic time warping, and the oblique lines correspond to represent the path that I just mentioned, you can see, for example, if you can see my pointer, that this area in gray is just this area in black, but that's been stretched, and this is indeed recovered by the dynamic time warping. So there is an alternative way to phrase dynamic time warping. So kind of the one with paths is classical, but there's also another one where we see rho as a matrix A, where the element ij is 1 if and only if ij is in the image of rho, so if it's traversed by rho, and 0 otherwise. So if we look at the set of realizable matrices, so admissible paths, and again you have a cost function, then we can write the dynamic time warping discrepancy as the minimum of a scalar product between A and the cost matrix C. And similarly, A star, so the matrix which corresponds to an optimal rho star, is given by the argmin of that same scalar product. So to show you a representation of that, here consider two curves C and Q, which are pretty similar. So in the bottom left figure, so figure C, you can see the matching as depicted, the path as depicted previously. And in B, you can see this warping matrix, so the representation of what another representation of which is in C. So we're starting from the bottom left. So let's say element 1, 1, and we're going to the upper right corner. And the row corresponds to the position in Q, and the column corresponds to a position in C, and the elements in gray are the ones for which are traversed by the path. So to move on to how we compute the dynamic time warping, well, actually, it's an example of a dynamic programming problem where we can divide the problem of matching U and V into problems of matching vectors up to Ui Vj. So the first I coordinates of U to the first J coordinates of V. And the cost will be represented by the entry ij in the matrix that we construct recursively or iteratively, depending on how we choose to do it. And so the dynamic time warping discrepancy is given just by the last element of that matrix, so entry mn. And it's actually pretty nice, because from that matrix we can also recover the path, so A star, pretty fast. So to move on to applications, the first one that is, I think, very much related to my thesis, so this project and what I'm trying to work on now, is based on the following observation. If we have a periodic pattern, then let's say we consider two vectors, one where we discard the first t coordinates and one in which we discard the last t coordinates. Then, if it's t periodic, the distance between the two should be small. And so this observation was used to propose an algorithm to detect patterns in string by considering the function which maps k to the dynamic time warping discrepancy between these between such vectors. So where we chop off the first k coordinates and the last k coordinates, and then simply set an estimate of the period to a local minimum. So you can see an example, for example, of such a pattern here, where what's in blue is the pattern that we would like to detect, and the rest is so in red we have another realization of that pattern, and same in black. And so hopefully the dynamic time warping distance would be more resilient to that than direct comparisons. So this was proposed for the Adama distance and characters. Now let's look at something which was proposed for real valued data. So in different contexts. So this is for time series classification. And the idea is to devise again an alternative version of dynamic time warping using similar ideas. So we have two input time series, and for each of them we will look at the sliding window embedding. And so for each time step we'll have a window of samples corresponding to neighboring samples of the sample we're looking at. And on that window, we compute a collection of shape descriptors. You can think of discrete wavelet transforms, Fourier decompositions, derivatives. And then instead of comparing the amplitudes of the time series as we would do in standard dynamic time warping, in shape dynamic time warping, we compare the descriptors of those sequences. So each of these descriptors comes with a metric, and we compare them as the sum of there's a metric which is the sum of the metrics on each of those descriptors, and we can use that as our cost function for the dynamic time warping. So with these promising ideas, people have also tried at looking at whether dynamic time warping discrepancy can be differentiated, because then we could do many things that were done. So, for example, there was the idea of Reise means, where people would look at what's the mean of a set of curves. Well, we can use the alignment to compute, so these paths to compute, to kind of recover a mean. But another idea was to maybe try to learn it, and for this, well, we would need differentiability. I mean, one way to tackle this is differentiability. One approach proposed by authors last year was DTW layer, which consists of learning kernels. So learning one of the, so when we have the discrepancy between x and y, so basically learning one of the, for example, learning x, and feeding the residuals from the discrepancy forward to the second layer or kernel, and so on and so on. And here the authors propose to differentiate the discrepancy directly. And for the Euclidean metric, it works. With one caveat, which is that actually the gradient is discontinuous when the path changes. So the path can jump from, let's say, from one choice of path to the other, and so as long as we stick on the same with the same path, everything is differentiable, and the gradient is well behaved. But when we change paths, it's not. And this is one of the motivations for the soft DTW, which was introduced by Couturier and Blondel in 2018, and relies on the idea of the soft min instead of the hard min. So for real values a1, ak, the soft min is defined as follows. So for a gamma greater than 0, it's defined as the minus gamma log of the sum of exponentials of minus ak over gamma. And so when gamma converges to 0, for example, we recover the ordinary minimum. And with this, so soft DTW was proposed with simply replacing the standard minimum with the gamma minimum of the cost. And before we compute the gradient, we actually need to look at the probability distribution on the alignments induced by these definitions. So one can notice actually that there will be a probability distribution induced by so proportional to the exponential of minus the scalar product over gamma. And the authors introduce what they call the expected alignment. So we take all possible alignment and compute the expected one with respect to that distribution. It's actually not that hard to compute. I mean, yeah. Once we have this distance matrix D from the dynamic programming, it's very fast. And so with this, we can compute the gradient of the soft DTW with respect to U if the cost is differentiable. And we can also look at the properties of the soft DTW. And it turns out that it's not so well behaved. So for example, for the Euclidean cost, we have some problems like if we look at the distance between, the cost matrix of x and x, it's not a stationary point of the function in one. So the function which maps y to the soft DTW gamma of the cost between the two. And also it happens that the soft DTW between x and itself can be smaller than 0, and even worse for unless very degenerate cases, but in principle, when we take gamma going to infinity, the distance goes to, the discrepancy goes to minus infinity. So it's not really well behaved in that sense. And so the authors follow up with work on soft differentiable divergence, which they, using the same principles, they introduce divergence, which, as they show, has better properties. So what does it mean for me? Well, to recall the aim, I would like to use, I would like to have an estimator of the velocity. And my current idea is to use dynamic time warping and the advances that have been made since its introduction to that aim. One idea is to leverage the work on pattern detection, but for real valued sequences of data. And this is what I'm currently doing now. I would like to also extend pattern detection to maybe segmentation or pattern learning in general, which is possible and shown to be possible with these differentiability ideas. Extend this to segmentation, so to find such patterns that I can really say that my signal is a concatenation of a pattern. And finally, as we've seen in shape DTW, dynamic time warping doesn't have to be done only on the amplitude or element-wise. It can be done, for example, on sliding windows. And I believe that the idea that was presented there could be used to, alongside geometric or topological signatures. And with that, I believe I thank you for your attention and I wait for questions.